Hi, this is Jack Jackson. In this video, we're going to talk about transformations and how they relate to conic sections. Conic sections are actually an interesting collection of geometric figures that have been studied intensely since the ancient Greeks. Apollonius of Perga, who lived in about the 2nd century BCE, is one of the first to write a major treatise on conic section called Conics. Conic sections are studied in pre-calculus, geometry, and calculus, particularly in calculus 2 in a lot of places. We start with a full double circular cone, and it's found by taking a line and rotating it about an intersecting line. The intersecting line is the axis of rotation, and then the other one is the generating line. And thus the cone is actually generated by a transformation. Conic sections can be produced by intersecting this full double circular cone with a plane, hence their name. In this section, we will give some basic definitions as examples of conic sections and see how our general results on transformations of relations apply to these. In particular, we will view ellipses as transformed circles. While a deeper study of conic sections could make an excellent additional chapter or playlist for this text, our focus here is on using them to illustrate how transformations connect to precalculus and calculus. They give another class of good examples of graphs of relations, quadratic polynomial relations in two variables, to which we can apply the transformations of formulas and graphs that we studied in the previous sections. Notice that we are taking a primarily analytic approach to studying conic sections, unlike the synthetic approach used by Apollonius and other ancient Greek mathematicians. Here is a GeoGebra activity that deals with conic sections. Okay, so in this one we can see here a cone, right? So it's like an ice cream cone but doubled and extending forever, right? Okay, so if we take a plane and slice it here where it's perpendicular to the axis, we're going to get a circle. So we're looking at this from the side, but if you look at it from the top, you can see that's a circle. Okay, and if we move this up, let's see, this one changes the angle between the generating line and the axis, which adjusts the cone, and then this one moves the plane up and down. So notice those are circles. It can degenerate down to a single point if it just goes through the vertex there, but we get a circle. Now what happens though if we rotate that just a bit? If we rotate a bit and then move it up or down, notice what happens now is we get an ellipse. Okay, and if we again continue to move that up and down, we can get that. If we change the angle a little bit more, we get a more eccentric ellipse, more elongated in one direction than the other. And if we do it a bit more, now the ellipse has morphed into a parabola. Okay, moving that up and down, we get a parabola here. Down here, it's intersecting the other part of the cone there. Okay, and if we tilt our plane a little bit more, it will actually intersect both parts of the cone, and we get a shape called a hyperbola. Okay, and it is possible for this hyperbola to degenerate to two line segments if it happens to go right through the center through this vertex. It is possible to get it to get just one line segment. I'm not sure if I can figure out a way to get this rotated just the right way. Okay, I need to rotate a little more. Okay, somewhere about right there. Oh, I had it for just a second. Then the plane is actually tangent to the cone. For example, it might contain that generating line and be tangent to it, so you could get a single line there. Okay, so those are the basic ways you can get a conic section. Okay. This is another graphic that kind of shows how you get a circle, parabola, ellipse, hyperbola, and then the degenerate ones, a point, a line, or two intersecting lines. So now I also have another GeoGebra activity, and this was one I created. And in this one, well, I'm just gonna pull it up and show it to you. I have it here. We talk about the various different conic sections. So I'm going to start by setting A to be 0 and B to be 0. Okay. Actually, we're going to start A to be 1 and B to be 1. That's what I really want. And this gives us a, when I click on ellipse, this gives us actually the unit circle. X squared plus y squared equals 1. And here's a point on the circle that we can move around. Of course, the circle is a set of points in a plane that are equidistant from this given point called the center. It has infinitely many lines of symmetry, including both the x and the y axes. Okay. It can be completely contained in this little unit, this square that is actually 2 units on each side, where it goes through 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Okay. Now, if I take this and apply what we've talked about before in transformations, if I replace x by x divided by a, we get a horizontal stretch or compression. Remember, the technical term for that is a horizontal strain. Now, of course, that's no longer a similar figure. It's no longer a circle, but it is an ellipse. And so one way we can think of an ellipse is just a transformed circle. And if we replace y by y divided by b in the formula, we get a vertical stretch. Now, some mathematicians insist that a is bigger than b. I insist that a is always the one that goes with the x, and b is the one that goes with y. And so we can see that that this has a horizontal radius, in this case of 5, and a vertical radius of 4. Okay. Now, we can also replace, after doing these strains, separate strains in the vertical and horizontal directions, we can now do a vertical and horizontal shift too. So we could say, for example, if h is, say, 2, we can shift to the right 2. Let's let k be 1. We shift up 1. So notice the center is now going to be at hk. Okay, we have some lines of symmetry. There are 2 of them. A vertical line of symmetry going through hk, in other words, x equals h, and a horizontal line going through that center, y equals k. And so you can see that as a transformed ellipse. The ellipse is a transformed circle. Here's the general form of it, x minus h squared over a squared plus y minus k squared over b squared equals 1. So we started with x squared plus y squared equals 1, replaced x by x over a, so that it became x squared over a squared plus, and then do y by y is replaced by y over b, so this y squared over b squared, that's going to equal 1. Then we replace x by x minus h and y by y minus k, and that does the transformations just as we just saw them. So notice we have this little reference box around it. That'll be interesting in a minute. Actually a little bit more interesting when we get to hyperbolas. But we have this here. Now, it turns out that there are actually 2 points called foci. Here they are in this particular case. There are 3 to the left and right of the um, center. Now, notice they're going to be on the major uh, diagonal here, okay, the major axis, because the one that's longer. So if A is longer, they'll be horizontally to the right and left. We'll call this distance C from here to here. In this case, C is 3. So this is going to be at H plus C, comma K, and this is going to be H minus C, comma K. But if B is the larger one, let's just do this by making A smaller. Once A gets smaller than B, now the focus is on the vertical one here because that's the longer one. Okay, and again, the distance from the center up to here looks like it's in the vicinity of 2.46 is the C value. Okay, let me go back to just because it works out even now. If the A and the B are the same, then this ellipse degenerates to a circle. So let me make it where they're almost the same. So it's not quite a circle, it's an ellipse. Okay, notice it has the 2 foci, and it's pretty round, pretty much like a circle, but not quite. If we let this, the closer we let this get to the same A and B, then what happens is these 2 foci get closer and closer to the center. The C gets close to 0, and the thing looks more and more like a circle. Let me go ahead and put like something real small, 4.001. Now see, notice that they're very, very close together. Very hard to tell this apart from a circle. But if you ever get the A and the B to be the same, then you actually get it degenerates to a circle. So you can think of a circle as a degenerated ellipse, or you can think of an ellipse as a transformed circle. And we get this. So in a circle, we would say it's an ellipse. It is a type of ellipse, but where the 2 foci and the center point are the same. But let's go back to one, say like this, for example. So that is a basic ellipse. Again, this particular one is then x minus 2 squared over 5 squared plus y minus 1 squared over 4 squared equals 1. If you were to multiply all this out, combine like terms, set it equal to 0, you would get this equation right here. 16x squared plus 0xy plus 25y squared minus 64x minus 50y plus minus 311 equals 0. In general, conic sections are quadratic relations in 2 variables x and y, and they could potentially have all of these terms with these different coefficients. Okay. If you want the ellipse to have a vertical and a horizontal axis of symmetry, then there will not be an xy term, or its coefficient will be 0. Okay. If you do this in parametric form, then it has a pretty nice parametric form as well. It's h plus a times cosine of theta, and y is k plus b times sine of theta, where theta is kind of an angle in here, or just t for instead of theta for a parameter. So in our case, this is 2 plus 5 cosine of t is x of t, and y of t is 1 plus 4 sine of t. In this form here, we call the coefficients, this is a, b, c, d, e, and f. So this is a is 16, b is 0, c is 25, c is negative 64, IBC, no, d is negative 64, e is negative 50, and f is negative 311. So it turns out if you take b squared minus 4ac, in this case you get a negative 1600. On an ellipse, this discriminant will always be a negative number. Now notice the if there is no b term, this just means that a and c have the same sign. So if the x squared, assuming there's no xy term, if the x squared and the y squared have the same sign, then you're going to end up with an ellipse. If they're not only the same sign, but actually the same number, that's whenever you have a circle. So notice those were exactly the same for our circle. Now, it turns out there's a nice Pythagorean relationship among this lowercase a, b, and c. Okay, so this distance from here to the focus, from the center to the focus, is c. Well, the vertical distance here is b. Now that's the shorter of this b and this a or b in this particular case. But it turns out that the distance from this, we'll call it a vertex, to this center, the leftmost point to the center, is a, in this case 5. And that's the same as the hypotenuse of this right triangle here. So we got a nice Pythagorean relationship that says c squared plus b squared equals a squared. Or if you have this one is the smaller one, it is b squared equals a squared plus c squared. But either way, if you solve for c, it's either a squared minus b squared or b squared minus a squared. If you take the absolute value, you get it correctly, and then take the square root. So in this case, the square root of 7 is the distance to the focus. Okay, if I go back, I picked 5 for purpose to make that really nice, so that the c is the square root of let's see, 5 squared is 25, 4 squared is 16, 25 minus 16 is 9, square root of 9 is exactly 3. So the distance to the focus is exactly 3. And the distance to this one focus, the distance to that focus is exactly 3 as well. Now, there's something called the eccentricity that sort of measures how elongated the ellipse is. It's always going to be less than 1. Well, let's see what happens if you put in a circle. It goes to 0 eccentricity. And if you get bigger eccentricity, it's going to be more elongated in one direction than the other. So that's going to be more eccentric. It's getting closer and closer to 1 because it's more stretched out in one direction than the other. A larger eccentricity, more eccentric. Okay, anyway, you measure the eccentricity as c over the maximum of a and b, whichever one's bigger there. Okay, now one more thing. So we're taking a pretty analytic approach here, so that we're looking at ellipses as just transformations of a circle based on their formula. But they have a geometric property that's interesting as well. If I take any point on this ellipse and I find the distance to this focus and distance to this focus and add them together, look what happens. At the moment, it's 10. If I go here, it's still 10. Notice it doesn't matter where I put this along here, it is 10. Okay, now of course it won't always be 10. If I change this to a different number, the difference is it's a different number here, but notice that this one, it's always 12. Okay, so it turns out that that is actually the geometric definition of an ellipse, that it's the set of points in a plane for which the given 2 points, called foci, it's a set of points in the planes for which the sum of the distances to those 2 foci is a constant, a fixed constant. Okay. Now, if you think about it, what is that constant? Well, it's the distance from here to here. Okay. Plus the distance from here to here, which is the same as from here to here. So it's really the same as the distance from this left point to the right one, which is twice A. Okay, or if it's whichever one's bigger. So like if this A is smaller, then the biggest place it's going to happen is down here. So it's going to be twice the maximum of A, and B is where that's going to be. Okay, is what that one is. Now, one other thing that's interesting, if I throw a tangent line onto this, okay, if you were to look at this angle right here, from the focus to that tangent line it makes with the tangent line, and you look at the angle from this focus to the tangent line, it turns out those two angles are the same, which means that if you made this into like a pool table, billiard table, and you were at this focus, if you shot the ball, it doesn't matter where it goes, when it hits this, if you're at the focus, when it hits the side, it's going to reflect back into the other focus. Well, this is used in certain places, like I don't know if you've ever been into a whispering gallery, but I've seen things like this, a room set up like this, or at least a shell set up on either end, where you can stand right here at the focus, say put your mouth or your head at this focus, whisper something. People in here cannot hear you, but because every sound coming off of that, no matter which direction it's going, whether it's going this direction, this direction, this direction, it's reflected back onto this other focus. So if someone is at this other focus, they're going to hear it clearly, almost as if they're standing right there next to you, whereas people at other places in the room maybe can't hear it at all. So there are some interesting reflective properties there that some of these conic sections have as well. Okay, I am going to show you on this one what happens if we rotate it as well. So here is, we can look at an angle of rotation, and here's the parametric form of the rotated ellipse down here. If we were to work this out in equation form like this, it would have a b term that's not, a b value that's not zero, an xy term that's non-zero. There's a way to go out figuring out the formulas for this, basically by doing a transformation of rotate, kind of figuring out what that rotation is. I'm not going to take time to go into that right now, but these can be rotated as well. Of course, now the axes are not vertical and horizontal, the axes of symmetry. All right, I think that's probably enough for this video talking about ellipses. In the next video, we'll talk a little bit about hyperbolas and then parabolas a little bit later. Okay.